Hi, this is your instructor, Mr. Pinter. Welcome to our lecture from Chapter 1. This video lecture will cover some of the topics from Chapter 1, such as units, scientific notation, algebra, graphing, and significant figures. We will not be covering the topic of motion in this video. That will be combined with the lectures for Chapter 2. In this course, we need to learn how to speak the language of science. The goal of science is to understand the natural world we live in. So you can think of two aspects of this. The first one is that we need to be able to describe the objects around us. We use descriptions such as size, mass, color, temperature, composition, etc. In order to do this, we are going to require units of measurement. The second thing is that we will be needing to find relationships that describe how objects interact with each other. Relationships in science are usually written as mathematical equations. So for example, later in this course, we will learn the famous equation called Newton's second law, which is F equals ma. This is a relationship between force, mass, and acceleration. So we're going to start off here in this course and in this first chapter by learning about units, scientific notation, algebra, graphing, and significant figures. So let's start by talking about pure numbers versus numbers used in science, which represent physical quantities. So, for example, in math class, you're almost always dealing with pure numbers. So if we, add 1 plus 1 to get 2, these are just numbers that we're adding here. The square root of 9 is equal to 3. This is another relationship between numbers. Or maybe we have an algebraic expression like x plus 2 equals 5, where we have to solve for x here, and we find that x is equal to 3. But again, these numbers don't necessarily represent anything here. They are just pure numbers. What we're dealing with in this class is physical science, which deals with numbers that represent physical quantities that require units, which tell us what the numbers mean. So for example, if someone asks you, what is the length of your car? And you tell them 4.6, well, that's meaningless because 4.6 what? 4.6 inches, 4.6 miles. Well, we're going to use, for length and distance in this class, we're going to use the unit of meters. But so we could describe the length of a car as 4.6 meters. So here the number 4.6 represents something physically. It's not just a pure number, and it's not a number because it's attached to the units of meters. Likewise, the time to eat a snack, 60 seconds, so this tells us the unit of time. The mass of a bicycle might be 12 kilograms. So these are three commonly used units that we're going to be using quite often in this course, and we're going to see many other units as well as we go through the course. Most of what we're going to do in this course is using a system of units called SI units, which is actually French for International System of Units. And these are also known as the metric system of units, which you've probably heard. So I'm just want to briefly introduce this system of units. We just mentioned on the last slide, for length, distance, or height, we're going to almost always use the meter. And the meter has a symbol of M. For time, we will measure time in seconds. Now, sometimes we may see times listed in minutes or even hours, and in that case, we may have to convert to seconds to do our calculations. And the symbol for the second is just an S. We'll introduce the concept of mass later on, and mass is measured in kilograms. The symbol here is kg, and we'll learn shortly what this prefix here, kilo or kilo, means 1,000. So this is actually 1,000 grams. But the unit here of mass is not the gram, it's actually the kilogram or kg. For volume, there are a couple of metric units. One of them is the liter, which has a symbol of L, and the other is the cubic meter, or meters cubed, as is shown here, meters to the third power. Later in the course, we'll learn about force, and force is measured in units of newtons, which is symbolized with an N. And for Newton, energy will be measured in units of joules, which has a symbol of J. Power has the unit of watts, which has a symbol W. And so this is just it's actually kind of a short list. We're going to learn about quite a few units in this course, but this is gives us an idea of sort of what we're dealing with here. And again, the kind of the main message here is that when we study science, particularly a physical science like this, we need to measure and quantify things, and in order to do that, we need to assign units to the numbers. Oftentimes in a science class, we deal with numbers that are either really big or really small. For example, later on in this course, we'll be learning some things about astronomy, and we're going to be dealing with huge numbers in the billions or even trillions. Also, in this course, we're going to be dealing with things that are extremely tiny. For example, we're going to learn about the atom, and we're going to learn about the nucleus of the atom, where things are extremely small numbers. So in this, because these numbers are difficult to write out when they're really big or really small, because there's so many zeros, we use something called scientific notation, which I'm sure you've seen before. You probably learned about scientific notation in high school. Scientific notation is based on powers of 10. And so this is just sort of a review of scientific notation, but we need to make sure that we are fluent in using scientific notation because, as I mentioned, we're going to be using it quite a bit to describe things in this course. So the powers of 10 means that 10 to the first power is just 10. 10 to the second power, or 10 squared, is 10 times 10, which is 100. 10 to the third power is 10 times 10 times 10, which is 1,000. 10 to the fourth power is 4 powers of 10, which is 10,000, and so on. So you can see there's a pattern developing here. The power of 10, the exponent here, tells us how many zeros there are after the 1. So 10 to the first power, there's 1 0. 10 to the second power, there's 2 zeros. 10 to the third power, 3 zeros, and so forth. Down here where we see 10 to the sixth power, which is 1 million, by the way, that is a 1 followed by 6 zeros. So instead of writing out something like this, 1 million with all these zeros, we're just going to say 10 to the sixth power. So this system here can be used with any number. It doesn't have to be just a power of 10. So for example, let's say we want to take this number 300 and convert it to scientific notation. So 300 is 3 times 100, and remember 100, we can look up here, is 10 squared. So we can write 300 as 3 times 10 to the second power. The number 420, well, this is a little different. We have this, we're still going to use 100 as our multiplier, but now we have 4.2 times 100. And so our number in scientific notation is 4.2 times 10 squared. Now, the main convention for writing numbers in scientific notation is to always have one number over here on the left, to the left of a decimal point, and all the other numbers are decimals after the decimal point. Okay, so like this, let's take this next number, 6,273. What we do, remember the rule is we have one number in front of the decimal point. So we have 6.2 0.273, all right, we put the decimal point right here, and then we have to multiply that by 1,000, right, because we're talking about thousands here. So our number is 6.273 times 10 to the third power. This number here, this is actually 7,500,000,000, all right, lots of zeros. Well, the rule again is we put the decimal point after the first number here. So we put it after the 7. So we have 7.5, and what we can actually do here is you can count how many zeros or how many places go after that. In this case, it is 9, so it's 10 to the 9th. So this number is written, is expressed as 7.5 times 10 to the 9th power. Another way to think of this, if we go back to this number here, 6,273, one thing we can do here is, remember, we're going to put the decimal point after the 6, all right? We always put it after the first digit, and then we just count how many we have to go over. So we count 1, 2, 3 to get to the end of the number, and that tells us that it's 10 to the third power. So in this one here, we're going to put the decimal point after the 7, and we have to now count how many places to go all the way to the end. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's how I get 10 to the 9th power. Now we can of course work backwards. By the way, these numbers here on the left up here are called expanded form, and the numbers on the right that we converted them to are, in scientific notation. So now we're going to work backwards. We're going to start with a number in scientific notation, and we're going to write it in expanded form. So if we have 5 times 10 to the third, well, that we can just write that as 5 times 1,000, using this here, 10 to the third is 1,000, which is 5,000. If we have 1.3 times 10 to the fourth, that's 1.3 times 10,000. Okay, and that is equal to 13,000. If we have something like this, 8.79 times 10 to the sixth, well, we can write, there's two ways to do this. We can write it as 8.79 times 1 million, right? 10 to the sixth shown right here is 1 million, and that's 8,790,000. The other way to do this is we can start with this number here, and we know we have 6 0. We have to move the decimal we have to move the decimal point here 6 places to the right. So if I start here where the decimal point is between the 8 and the 7, I count over 1, 2, 3, 4, 5, 6, and then I fill in all those spaces with zeros to get the same result here. So the previous slide dealt with scientific notation for large numbers. We can do the same thing for small numbers. And here again, we're going to use powers of 10, but notice here the powers of 10 are negative. So 10 to the negative 1, remember a negative exponent is the same as a reciprocal, meaning this is 1 over 10 to the first power, which is 1/10 or 0.1. 10 to the minus 2 is 1 over 10 squared, which is 1/100th or 0.01. 10 to the minus third is 1 over 1,000 or 0.001. So again, you can kind of see the pattern developing here. Basically, the exponent here tells us how many places the decimal has moved over. Okay, it's and so we fill those in with zeros. So 10 to the minus 6 down here is 1 millionth. So there's a decimal point here, and now we have 5 zeros because if we count over 6 places, 1, 2, 3, 4, 5, 6, we always have the decimal point over here to the right of the 1. So let's convert some numbers from expanded form to scientific notation again. So the number 0.03, well, that's 3 times 0.01, all right? just multiplying these together here. And so that can be written as 3 times 10 to the minus 2. There's another way to do this. We can just start with our pointer here at the decimal point, and notice we have to move the decimal over to the right 2 times to get it after the 3. And so that tells us what the exponent is here. It's minus 2. For the number 0.042, again, there's 2 ways you can think of this. It's either 4.2 times 0.01, which is 4.2 times 10 to the minus 2. Or, again, we can take this decimal point, which is right here, and we can move it over twice to put the decimal between the 4 and the 2, where it is here. And that moving the decimal twice means we have 10 to the minus 2 power. This one here, 0.0006273. Well, I'm showing how to do that here. What we can do is count how many places we have to move the decimal so that it ends up between the 6 and the 2. So we move it once, twice, 3, 4 times. So we have 6.273 times 10 to the minus 4. The number 0.00000075, that's the same as 7.5, and we have to think about how many places do we move that over. Well, we're starting here. We're going 1, 2, 3, 4, 5, 6, 7 places over, so that's how I have 10 to the minus 7 there. And of course, we can work backwards. We can start with a number in scientific notation, and we can write it out in expanded form. So the number 5 times 10 to the minus 3, we can write as 5 times 0.001, which is 0.005. The number 1.3 times 10 to the minus 4 is 1.3 times, and we can look up here on the chart, 10 to the minus 4 is 0.0001. And multiplying those together, we get 0.00013. Let's do another one, and I'll show you, kind of a trick again. If we have the number 8.79 times 10 to the minus 6, well, one way to write this is start with the number here. Here's our original number, 8.79, which is this number here. And we have to move the decimal place 6 places to the left. So what I do is I count over 1, 2, 3, 4, 5, 6, and put the decimal right there and fill in all the zeros there. So I end up with 0.000000879. Here's a couple more examples using scientific notation. So these on the left here are to start with an expanded form here and write them in scientific notation. So this number given here, this is actually 213 million. One way you can think of doing this again is the decimal is over here. You can think, all right, well, if I'm going to move that decimal point between the 2 and the 1, I have to move it over 8 places if you count. So it's 2.13 times 10 to the 8th. Likewise for this number, 0.00872, if the decimal place is right here and I need to move it between the 8 and the 7, then I need to move it 1, 2, 3 places, so it's 10 to the minus 3. Working backwards, expressing in a scientific notation in expanded form, so the number 5.6 times 10 to the 4th, we're starting with the decimal place here between the 5 and the 6, and we're going to move it over 4 places. So we have to pad those places with zeros to get 56,000. Likewise, 9.71 times 10 to the minus 5, the decimal point is originally between the 9 and the 7 over here, and because it's a negative exponent, we're going to make this a smaller number, so we're going to move the decimal point to the left 5 places, filling in the zeros. So you may have learned your own methods of the tricks of how to write numbers in scientific notation, but usually it's a matter of either looking at the table or just counting the decimal places. One thing I would highly recommend and almost demand for this class is that you get yourself a scientific calculator. This doesn't have to be a big investment. And it doesn't have to be a fancy programmable graphing calculator or anything like that. The one I like to use is a Casio FX260. It's a solar powered calculator. It has the solar panels right here, so you never need batteries for it. It just runs on light from in your house at your desk. And the great thing is the price. You can get them for about $7, for example, on Amazon. But it's a scientific calculator, so it has all of the scientific functions that we're going to need for this class, and you can certainly use it for your other classes as well. So regarding scientific notation, you'll have to learn how to use whatever calculator you end up buying. You may already have one from high school. Be sure that you know how to use scientific notation on this calculator. Let me show you an example here for this particular calculator. If you wanted to type in the number 1.5 times 10 to the 5th, the way you enter that in this calculator is, you would push 1.5, and then to get the exponent, you press this key down here. On this calculator, it's called EXP for exponent. You press that button, and then you would enter the 5 up here. You notice you don't have to put the 10 in there. You just enter the power, and it looks like this on the calculator. It's 1.5, and this 5 up here tells you the power of 10. So this number here is actually this number here, 1.5 times 10 to the 5th power, which is 150,000. All right. On your calculator, it may not be called EXP. I've seen some calculators, it's called EE. And again, your job is, if you don't get one of these calculators here, if you have a different calculator, you absolutely need to figure out how to work with scientific notation. Another example here, if you wanted to enter the number 1 times 10 to the minus 3, you would enter, again, 1.0, press the EXP button again, this button down here, and then you would hit this plus minus button right here. This puts in a minus sign. You can see it in front of the 3, and then you enter the 3, which is the power. So you can see here it's 1.0 to the negative third times 10 to the negative third power. So once you get your calculator, or again, if you already have a calculator that you're going to be using, I want to show you some arithmetic practice that I want to make sure that you can do these problems on your calculator. So even though these may look really simple and basic, make sure that you can do all these problems here and get the correct answer, because this will ensure that you're pressing the right numbers and the right order on your calculator. So for example, this is 14 times negative 3. You should get negative 42. And again, the way you put negative numbers in on this particular calculator, you use this button right here, the plus minus button, to make, you would press that before you would put in the 3. This is another one that a lot of students make mistakes with. That if you have an expression 84 divided by 12 times 3.5, all down here in the denominator, do this on your calculator and make sure you get the correct answer of 2. A lot of students will type in 84 divided by 12 times 3.5, and that is not correct. The correct way to do this on your calculator is 84 divided by 12 divided by 3.5, or use parentheses around these two numbers if you're going to multiply them. So either way, make sure that you get this right number so you don't make this mistake on the homework or on a quiz. Know where the square button is. All right, 75 squared. On this calculator, you can see it right here. It says x squared. So that's the number you press to square something. Likewise, find out where the square root button is. Make sure you can figure out the square root of 75. On this calculator, you'll see it right above the square button. So to access the square root, you press Shift and then the square button. That does the square root of this number 75. The reciprocal button is sometimes useful, so you can tap in 0.32, and then if you look here, let's see, I need to find it here. It looks like it's right here. This 1 over x on this calculator is here, but again, this may be a different button on your calculator that you're going to use. But that button takes the reciprocal of whatever number you put in there. Another one that you're going to need to use is the power button. So if you want to do 15 to the 3.5 power, this is the correct answer, by the way, make sure you can do this on your calculator. On this calculator, that is done here with the x to the raised to the y power. So you would actually type in 15, press this button, and then type in 3.5, and then the equal sign. So you might want to be pausing this video right now and go through these and make sure you're getting the right answer. If you're not, please figure out how to do these correctly on your calculator. Ask for help, or you can ask me if you can't figure it out. Scientific notation, make sure that you can do these problems on your calculator using scientific notation. And what makes some of these tricky is there are minus signs. This one has a minus sign in front of the number out front. This one has a minus sign here, and it has a minus sign in the exponent. And so make sure that you can add, subtract, or multiply, or even divide. This is a division problem down here in scientific notation, and make sure you're getting these correct answers. So this will, it sounds like, a little bit of busy work right now, but make sure you can do these problems on here, and this will save you a lot of headache later. Let's now talk about what are called metric prefixes. So this is a table here that shows a list of most of the metric prefixes. There are others, they keep going past what this table shows, but those are used much more rarely. So for example, the prefix deca means to multiply by a power of 10. So in other words, a decameter is 10 meters. All right, a decaliter is 10 liters, and so forth. A decagram would be 10 grams. And you can see that, the prefix is deca. It has a symbol here, DA. This one is not used, surprisingly, this one is not used that often. Likewise, there's one called hecto, which means 100. So a hectogram is 100 grams. Kilo, this is one that's used a lot. Kilo is 1,000. So a kilogram or a kilogram is 1,000 grams. Okay, a kilometer, or we say kilometer, is 1,000 meters, etc. And kilo, you can see, has the symbol K. Mega is another one that's used quite often. Mega means 1 million. That's 10 to the 6th power. And mega has a symbol of an uppercase M. It's important to use the right case here. It's case sensitive because notice lowercase m means milli, which is 1,000th. So that's very different than mega, which is 1 million. And then it goes up from there. Giga is for a billion, and tera is for a trillion, which is 10 to the 12th power. And then we can also use these prefixes for smaller quantities. For example, deci, not to be confused with deca, is 1/10. So a decigram is 1/10 of a gram, a deciliter is 1/10 of a liter, etc. Centi, that one is very common. For example, the centimeter, right, is 1/100th of a meter. So centi means, or has a symbol of lowercase c. Milli, as I mentioned before, it sounds like that would mean 1 millionth, but it doesn't. It means 1,000th. It's 10 to the minus 3rd power. And milli is abbreviated with a lowercase m. Micro, which is 1 millionth, actually has a Greek symbol. It's the mu symbol. The lowercase Greek mu stands for micro, which means 1 millionth. So a micrometer, for example, which is also called a micron, is a unit of length equal to 1/1,000,000th of a meter. Nano, you've maybe heard that one. That is for something that is 1/1000,000th. So a nanometer, which is something that we're going to use to measure the wavelength of light, is a very small unit of distance. A nanometer is 1/1000,000th of a meter, and a nanometer would be abbreviated nm. And the smallest one I show here is pico, which is 1/1000,000th, 10 to the minus 12. So let's just do a couple examples here so you get the feel of this. So 2 kilometers. Well, kilo, remember, that means 1,000. So first of all, we can...
having some trouble with the connection.
Oops, excuse me. We have 2 kilometers. Let's abbreviate this first with K for kilo and M for meter. So 2 km, or 2 kilometers. Well, remember, kilo is 1,000 from up here in the table. So that's 2 times 1,000 meters, which is 2,000 meters. And if we want, we can even write that scientific notation as 2 times 10 to the third meters. 5 centimeters, or 5 cms. Well, centimeter is 1/100th of a meter. So it's 5 times 0.01 meters, or 0.05 meters, which is 5 times 10 to the minus 2 meters. 15 milliseconds, or 15 ms. Well, remember, milli, if we look up here in the table, is 10 to the minus third, or 1,000th, 0.001, which I wrote here. So this is 0.015 seconds, or in scientific notation, 1.5 times 10 to the minus 2 seconds. 3 nanometers, or 3 nm, is, again, a nano, remember, is 10 to the minus 9, all right, or 1/1000,000th. And so this is going to be, we're going to have all these zeros here. So we have, this is 3 billionths of a meter. Or we can write it in scientific notation as 3 times 10 to the minus 9. I think I have a typo here. This should be a minus 9. Sorry for that confusion there. Let's do just a couple more here. 14 megaseconds. Well, remember, mega means 1,000,000. So this is 14 million seconds, or 1.4 times 10 to the 7th seconds. 4.2 gigawatts. Well, giga, we can look up here. That is 1 billion, all right, or 10 to the 9th. So we can write it as 4.2 times 10 to the 9th watts. So let's just do a very quick review of algebra. The reason for this is that mathematics is a very powerful tool to use in physical science, especially in a science class like this, a physical science where we are going to rely on measurements and data and quantitative data to describe things with numbers. So we're going to need mathematics. In fact, we'll learn later that Isaac Newton actually invented calculus to help him solve physics problems that he couldn't solve with algebra. The good news for us is that we won't have to use any calculus in this class, but we will be using a lot of algebra, and we'll be doing algebra in just about every lecture in this course. So this is not a math class, so I'm not going to go through a bunch of algebra with you guys, but I would like you to just do some quick review. These are 4 problems here that you should be able to solve using really basic fundamental algebra that you learn in high school. So if you see something like 3x minus 2 equals 7, you should know how to solve this, right? You have to get the x all by itself, so you can add 2 to both sides, to get 3x equal 9. You can divide by 3 to get the answer x equal 3. So make sure you remember how to do this. This expression here, d equals 1/2 at squared. This is actually a formula that we're going to encounter pretty early on in the course. You should be able to solve this for t, which represents time. And to do this, again, you have to get the t all by itself. Get rid of the 1/2 by multiplying by 2. Divide by a. and then take the square root. So you should get t equals the square root of 2d divided by a. Something like this expression, mgh equals 1/2 mv squared. You should be able to solve this for v. All right, even though we don't have any numbers in here, you can still solve it. You should be able to realize that you can simplify this by canceling the m's on both sides, and then isolate the v squared, take the square root, and you should get v equals square root of 2 times g times h. And then something like this, we're going to encounter this equation later on in the course. P squared equals r cubed. You should be able to solve for both p and r, and those expressions are shown here. We'll actually go over this one a little more carefully later on in the course, but these are the types of basic things that you'll need to be able to do to be successful in this course. So if you're rusty on your algebra, or if algebra was not your strength in high school, don't panic or get too stressed out yet. We're going to take things slowly in this course, and I guarantee you by the end of the course you will certainly be much stronger and better at math, in particular in algebra. The last slide here in our first lecture here is about graphing, and you're going to certainly have to be able to interpret graphs in this class. Because of the online nature of the class, you may not be making any graphs per se, but you'll have to know how to read them and so forth. So let's just take this example here. Let's say you take a hot cup of coffee and you stick a thermometer in there. It's a Celsius thermometer. And you measure the temperature, right after you pour the coffee, and then every 5 minutes you take and record the temperature of the coffee, and you do this for 25 minutes. So what you end up with is some data. For each time, 0 minutes, 5 minutes, 10 minutes, 15 minutes, 20 minutes, 25 minutes, you're going to measure and read a temperature here and record this. So let's say then we graph the temperature here as a function of time, and we can see that what's happening here is the coffee starts out at 90 degrees. After 5 minutes, right, this is the time down here, it's dropped to, it looks like 55 degrees. After 10 minutes, it's dropped to about 32 degrees. And then after 15 minutes, it's at 20 degrees, and so on and so forth. So this shows the trend of the coffee cooling until it reaches basically room temperature here, which looks like about 18 or 19 degrees Celsius. And then the temperature is stable. So this graph has a lot of the characteristics of a well-made graph. So let's just look at these real quickly. So a good graph should have a title. So the title is a description of what this graph shows. This graph is showing us the coffee temperature versus time. So the coffee temperature is this axis here as a function of the time down here. So the independent axis label, that's this here. So this is, notice this, we know what this graph refers to down here. It's time, and it's very important, of course, to have the units. The units here are minutes. These are not seconds or hours or days. Likewise, the dependent axis label, that's the one over here on the vertical axis. This is called a dependent axis because the temperature depends on the time. The time is an independent variable. That time just keeps ticking along. All right, that's the independent variable. The temperature depends on the time. So this dependent axis also should be labeled. We're talking about temperature, and the units here are degrees Celsius. And typically, again, those units are put inside parentheses, like you can see here. Notice that both axes are scaled with tick marks which have numbers. So we can see that, this is 5, 10, 15, 20. The temperature is going up by 10 degrees, 10, 20, 30, 40, 50, etc. Data points are clearly shown. Those are the black dots there. And optional on this graph, which is nice, we can see grid lines, this sort of checkerboard here. If you're using graph paper, obviously those are going to be pre-made. And then the other thing that's an option here, but it's nice, is a trend line that connects the data points. So in this case, there's a nice smooth curve that connects and shows, this sort of interpolates what the temperature would be in between our data points. We're sort of guessing that this would be a smooth curve like this. So this is an example of a nice graph. It's very clear, and everything is labeled correctly. It's very easy to interpret a graph like this when it's made correctly. So one of the first things we'll be doing in this course, in our next lecture, as a matter of fact, is learning how to graph motion, and we'll be constructing graphs, somewhat like this, to analyze the motion of an object. So that's it for Chapter 2. I will see you shortly when we begin Chapter 3. Goodbye. Let's return now to the subject of units. One of the things that we occasionally have to do is convert between various unit systems. Now, we mentioned earlier that in this course we are going to be using the SI system of units, or the otherwise known as the metric system. But occasionally we'll come across in a problem or an example where there are other units used. For example, the common English system units. So, for example, in English system, distances are measured in inches or feet or yards or miles. So we're going to have to basically convert those over to the metric equivalent. So, for example, 1 inch is equivalent to 2.54 centimeters. 1 foot is equal to 30.48 centimeters. 1 yard is 0.91 meters, and 1 mile is 1.609 kilometers. Also, for mass, the English system uses pounds. That will be converted. 1 pound is equivalent to 0.45 kilograms. And we can even convert something like miles per hour, a measurement of speed, to its metric equivalent is 1 mile per hour is the same as 0.447 meters per second. We'll talk about what speed and velocity mean later in the course when we get to Chapter 2. One more I'll just throw out here, this is a common one, is for volume in the English system, a gallon is equivalent to 3.79 liters. So in order to make a conversion, let's just start doing some examples here. So for example, let's say we're asked to convert 60 miles to kilometers. So what we do is, and by the way, this is shown in more detail in your textbook in one of these so-called tactics box, and you can look at this in more detail on your own. But basically, to convert 60 miles to kilometers, we start with the 60 miles, and we write that here again if you want to, and what we're going to multiply by is the conversion factor. Now, how do we get a conversion factor? Well, we just look at a table like this, or we can look it up and Google it or whatever. But we know that 1 mile is equal to 1.609 kilometers. So what we have to do here is we're going to multiply by the conversion factor. Notice we have 1.609 kilometers over 1 mile. These are the same things, right? This is the same distance. 1.609 kilometers is equal to 1 mile. So this fraction here is just 1. So this does not change the length of our measurement, it just changes the units. Now, how do we know to put the kilometer part on top and the mile on the bottom? Sometimes we do it in the opposite way. Well, the trick is we want the miles to go away because we're converting to kilometers. So if the miles are over here, basically in the numerator, they have to be in the denominator here. So we're going to put the miles down here, and we can see those cancel out. So our answer is 60 times 1.609, and notice the only thing that survives is the km, the kilometers. So we end up with 96.54 kilometers. And then if we, we'll talk about significant figures later. This would be rounded to 97 kilometers because our initial distance was given with 2 significant figures. Let's not worry about that part right now. Let's just do a couple more examples here so you can see how to do this, and it's pretty simple once you get the hang of it. So the next one, how many miles are there in a 10K race or a 10-kilometer race? So here we're going to go the opposite direction. We're going to start with 10 kilometers, and we're going to convert this to miles. So again, we're going to use the same conversion factor here. 1 mile is equal to 1.609 kilometers, but notice here we're putting the miles on top and we're putting the kilometers on the bottom because the kilometers have to cancel here. So this time we do 10 on our calculator divided by 1.609, which gives us 6.2, and of course the units here are miles. So a 10K race is 6.2 miles. Let's just do a couple more examples here. An American football field is 100 yards long. How many meters is this? So we're going to take 100 yards and we have to multiply it by the conversion factor of meters to yards. So again, we look on our table here, 1 yard is equal to 0.91 meters. So we put the yard on the bottom, okay, because the 1 yard, this yard has to cancel this yard. And we have the 0.91 meters on top. So we have 100 times 0.91, which you can do that in your head, is 91 meters. One more example. This one just involves a couple of steps, which is sometimes the case. I'm 6'4". So what is my height in meters? So the first thing we're going to do is figure out how many inches of height I have. So let's do the feet first. So 6 feet, technically what we're doing here is we're going to multiply 6 feet by 12 inches per foot. Okay, now that's not in the table here, but that's something I'm sure you know. And so again, you can see the foot here is going to cancel the foot here. So 6 times 12 is 72 inches. And then since I'm 6'4", I have to add the 4 inches to that. So my height in inches is 76 inches. So now let's convert that to meters. So if you look up here, there's no conversion from inches to meters. So let's do it in 2 steps. That's no problem. We start by writing our initial height here in inches, 76 inches. Let's now convert that to centimeters. So from the table, notice 1 inch is 2.54 centimeters. So I'm going to multiply by 2.54 centimeters per inch. Why did I write it this way? Because this inch here has to cancel this inch here. We need to get rid of these inches, all right? Now, the next thing, that's going to give me my height in centimeters, but of course we want meters. So I'm going to multiply by 1 meter per 100 centimeters, right? 1 meter is the same as 100 centimeters. So again, why did I write meters on top and centimeters on the bottom? Because this centimeter here has to cancel this centimeter here. We want meters for our final answer, so that has to be on top. So on the calculator, I'm going to take 76 times 2.54 divided by 100 to get my height, which is 1.93 meters. The last topic in this first chapter is significant figures. So significant figures, which are usually said sig figs, since it's a lot easier to say, are digits in a measurement that determine the accuracy of the number. The main purpose of using sig figs is to make sure that we don't misrepresent a number as having more precision or accuracy than it actually has. So to see why sig figs are necessary, let's go through a little example here. Suppose that you have a coin here. It's a, maybe some old antique coin, and for whatever reason you're asked to calculate the area, the surface area of the face of this coin using a ruler that you have, a millimeter ruler. So you know from geometry class that the area of a circle, which is our coin here, is equal to pi r squared. So we need to figure out what is the radius of this coin. Well, to figure out the radius, that's a little tricky because we don't know exactly where the center is. So we're going to measure the diameter of the coin here. And so we put this ruler up to the coin like this, and we sort of eyeball it the best we can. We're not going to, cheat and use a magnifying glass or anything like that. We're just going to sort of use our eyes, and we can see that the diameter looks pretty close to 40 millimeters, right? This is 4 centimeters is 40 millimeters, but we don't know for sure, right? It's close. So we know that the radius is half of that, which is about 20 millimeters. Now, the precision of measurement using our eyes, especially since this ruler is marked in units of millimeters, the closest we can get is basically 1 millimeter. So that is our precision. So this means the actual radius is somewhere between 19.5 and 20.5 millimeters. All right, that's what. So we're going to call our radius 20, but we know it's not exactly 20. It's somewhere in this tolerance here, in this range of values. So let's go ahead now and calculate the area of this coin. So remember, area again is pi r squared. So pi, if you punch up pi on your calculator, you usually have a key that has the pi symbol. It'll come up something like 3.1415926, and there may even be more digits shown. Pi goes on forever and ever. And then we're going to multiply that by the radius. We're going to just keep it in millimeters here. So we're going to put 20 and square that. So that's 400 times pi. And here's what your calculator will spit out, this number, 1,256.63706 square millimeters. So if you were to tell somebody that this is the area of this coin, this is very misleading. This suggests that we know the area with a precision out to 1, 2, 3, 4, 5 decimal places, but we absolutely do not know that type of precision. So the question is, well, what is the area then of this coin based on our accuracy and precision of measurement here? How should we write this number? So this is where we're going to use sig figs to come to the rescue and tell us how to write this number correctly that shows the precision or lack of precision in our measurement. So we'll return to this example a little bit later when we talk about doing calculations like this with sig figs. Before we actually get to the rules of working with significant figures, let's define some terms. And in particular, it turns out that there are 3 types of zeros that we can encounter in a number, and they all have different significance, no pun intended, when we deal with sig figs. So let's look at our first example here. Here's a number, 508,300. So first of all, the 5, the 8, and the 3 are obviously non-zero digits, okay? And so those will be important, as we'll see when we get to the rules. But what we're talking about now are these zeros. So this 0 here is called an in-between 0. Notice this 0 is in between a 5 and an 8. It's in between 2 non-zero digits. At the end here are what are called trailing zeros, okay? And it turns out that these are going to be treated very differently than this 0. Let's look at another example here. Here's a decimal number, 0.0050830. So now notice before we get to our non-zero 5 here, we have what are called 3 leading zeros, okay? And again, these leading zeros are very different than the in-between 0 here, the 0 that's between the 5 and the 8, and we have a trailing 0 at the end. So again, all these zeros here, they all look like zeros, but they are very different when it comes to significant figures. So when we get to the rules of significant figures, we'll see how to handle these 3 types of zeros. The method of working with sig figs can be summed up into 12 rules. And this sounds like a lot, but they're actually, most of them are pretty simple, and some of them, well, hopefully most of them are even kind of make sense. And you've probably learned about sig figs, previously. This is taught certainly in high school and sometimes even in junior high school or middle school. Some of these rules are taught. So it's nothing that difficult, but let's go through them so we can work with sig figs. So rule number 1 is that all non-zero digits are significant. So for example, the number 58, well, both the 5 and the 8 are significant. So this number has 2 sig figs, or 2 significant figures. figures. The number 4.52, again, there aren't any zeros here, so all three of these digits are significant, so we have 3 sig figs. Rule number 2 is that all in-between zeros are also significant. So remember, an in-between zero is the number 0 in between two non-zero numbers. So the number 7,059 has 4 sig figs because this 0 here is significant. The number 4.0807 has 5 significant figures because both of these zeros are in between zeros. Likewise, the number 10,002, this has 5 sig figs because these 3 zeros are all in between non-zero numbers here, and so all of these are counted as sig figs. Rule number 3 is that leading zeros are not significant. So this is different now. So the number 0.58 only has 2 sig figs. This leading zero does not count. The number 0.0009 has 1 sig fig. The 9 is the only significant figure in this number. The number 0.00404 has 3 significant figures. We ignore these 3 leading zeros and we count the 4, the 0, and the 4. Remember, this 0 here is significant because it's an in-between zero. The rule number 4, trailing zeros to the right of the decimal are significant. So the number 0.700, now here's our decimal point right here. These 2 zeros here, remember, these are called trailing zeros. These are significant because this number here tells us that this number is precise out to this 3rd decimal place. So we have to count them. So this is 3 significant figures. The number 5.0600 has 5 significant figures. All right, this is an in-between zero, which is always significant. And then here are the trailing zeros. They are also significant. So all 5 digits here are significant. This number here, 0.00090, has 2 significant figures. Those are the 9 and the trailing 0. These leading zeros here are not significant by this rule number 3. All right, let's continue. Rule number 5. Trailing zeros in a whole number with no decimal shown are not significant. So the number 70, all right, this is a trailing 0, but there's no decimal point here. So the only significant digit is the 7. So 70 has 1 sig fig. The number 5,000, as written like this, has 1 sig fig, and that's the 5 here. These trailing zeros, again, are not significant because there is no decimal point. The number 730 has 2 sig figs, just the 7 and the 3. Now look at rule number 6. Trailing zeros in a whole number with the decimal shown are significant. So the number 70 point means that this 0 is considered now significant, and this is shown because we put that decimal there. So this has 2 sig figs. The number 5,000 with a decimal, all of these digits are significant, including all these trailing zeros, because there's a decimal here. So this 5,000 has 4 sig figs, whereas up here, 5,000 written like this without the decimal point has only 1 sig fig. Rule number 7, exact numbers, which are also sometimes called defined numbers, have an infinite number of sig figs. And we'll return to this rule later when we start doing calculations with significant figures. But let's say if we're told to pick a number and then we're asked to double that number, well, we need to multiply the number by 2. Well, what we mean here is that this is an exact number 2. All right, so it's really 2.00000, and the zeros just keep on going forever. Likewise, the number pi is a defined number. All right, it is a 3.14159,265, and this keeps going on forever and ever again. So in this case, in this type of application, the 2 here and the pi here have an infinite number of sig figs because they're exactly precise numbers. Rule number 8 deals with scientific notation. So if you have a number like n times 10 to the x, okay, x is the exponent, the power of 10, and n is this number out in front, then all digits comprising n, the number in front, are significant according to the first 6 rules, all right, that we discussed on the last several slides. The 10 here and the exponent, whatever it is, are not significant. All right, so the number 7.2 times 10 to the third, the 7 and the 2 are significant digits, so we have 2 sig figs. 5.01 times 10 to the 7th, the only thing we look at is this, the 5.01, this is 3 sig figs. I won't go through all these, but this is just a list of over 20 practice numbers that you can kind of go through and make sure you understand the rules that we just went through. Let's move on to the next rule. The last 4 rules have to do with calculations involving numbers where we use sig figs. So rule number 9 says when we multiply, divide, or take square root, the number of sig figs in the answer equals the smallest number of sig figs in the calculation. So for example, let's suppose we're supposed to multiply the number 1.778, which has 4 sig figs, by times 15, which is 2 sig figs. So we do this on our calculator, right? And we get the number 1,667. But according to this rule, we have to use the smallest number of sig figs here, which is 2, and this number would be rounded to 1,700 because 1,700 or 1,700 has 2 sig figs. This number right here has 4 sig figs, and that is not correct because our accuracy or our precision is only good to 2 sig figs. So our answer must only have 2 sig figs. All right, so this is a misleading answer. All right, this is a little bit different here than you might be used to in dealing, with numbers and mathematics. Another example here, 1.33.50. All right, now this is 5 sig figs according to our rules. We're going to divide this by 0.00506. Remember, these leading zeros do not count, so this number only has 3 sig figs. So if we do this on our calculator, we'll get 26,383.4. However, remember we have to use the smaller of these 2 numbers, sig figs, so our answer has to have 3 sig figs. So we have to round this to 3 sig figs. So basically we have 2, 6, and this next third sig fig here rounds up to 4. So our answer is 26,400. So let's go back to our coin problem. Remember the example a few slides ago where we were trying to figure out the area of a coin, and we said the area is pi r squared, and we measured the radius to be 20, all right, to 2 sig figs. So I'm going to write 20 as 20 point. Remember that decimal point tells me that both of these are sig figs. If we just wrote it as 20, that would only be 1 sig fig, but we know it better than that. We know our accuracy here is to 2 sig figs. So on our calculator, again, we have this number here, 3.1415926. This is pi, but the important thing is this number here has the least number of sig figs. Remember, this number here has an infinite number of sig figs. So on our calculator, when we do this, the answer comes out to be 1,256.63706 square millimeters. However, according to our rule, we have to put our answer in terms of 2 sig figs, so we round this to two significant figures. So 1, and then the second one, the second sig fig right here, this 2 is going to round up because of the numbers after it to 1,300 square millimeters. So this is our answer here. This is the correct answer for our area, not this number here. And this answer here reflects the fact that we only know our area to two significant figures. We don't have any more accuracy or precision than that. Anything, written anything else, like if we wrote our answer as 1256, that would be misleading. Rule number 10. When adding or subtracting several numbers, the number of decimal places in the answer should match the smallest number of decimal places of any number used. So let's start with a subtraction here. We have 10.11 minus 3.6. Now, 10.11 has two decimal places, the 1 and the 1. 3.6 has one decimal place, just the 6 there. So when we do this on our calculator, we end up with 6.51 kilograms. But remember, the answer has to have the lower of these two numbers. So we have to use one decimal place. So we would round this to 6.5 kilograms. That is our answer. Over here, we're adding three numbers, 101.25 plus 3,536.2 plus 123.448. On our calculator, we get 3,760.898. However, we have to look at the least precise number here, right? This number in the middle here only has one decimal place. So our answer has to be rounded to one decimal place. So in this decimal here, the 0.898, we have to round that to 0.9. We round it up in this case because of this 98. Causes this 8 to round up to 9. So here's our correct answer here. Rule number 11 says when we're doing calculations with exact numbers, ignore the sig figs of the exact numbers since they have infinite sig figs. So for example, the radius of a circle is, let's say, given as 6.3 meters. Find the circle's diameter and area. All right, so when we talk about the diameter is twice the radius. But this 2 here, it looks, like this might only be one sig fig, but no, this 2 is an exact number because we're doubling the radius. It's precise. So we can ignore the fact that this has an infinite number of significant figures. Remember, we're using the number with the least amount of sig figs. So our radius, 6.3, has 2 sig figs. So 2 times 6.3 is 12.6. So we round that to 13 because we have to just have 2 sig figs. If we didn't use this rule here, you might incorrectly say, oh, well, this 2 has only 1 sig fig, so I should round this then to 10 meters, but that is not correct. Remember, the 2 is an exact number, so we can just ignore it and use the other number for sig figs. Likewise, we did one like this earlier. The area of a circle is pi r squared. So here's pi. Remember, it has an infinite number of sig figs, so just ignore that. All right, it's perfectly precise. What determines our answer is the r. It's the 2 sig fig number 6.3. So when we do this all in our calculator, pi times 6.3 squared, we get 124.68981 square meters, but we have to round this number to 2 sig figs because that's the least amount of sig figs in our calculation. So 124.6 rounds to 120 with just the 1 and the 2 being our sig figs. The 0 here, the trailing 0, is not a significant figure. And finally, we get to our last rule. Rule number 12 is that when we're doing calculations that require several intermediate steps, and this is often the case in physics, a lot of times the answer doesn't come that easily. We have to do a bunch of different calculations. So all of those intermediate calculations, we have to be careful to not use the sig fig rules or round numbers until the very end. The reason for this is if we start rounding and using sig figs on each step of the way, we may accumulate all of our round-off errors, and it can end up affecting the end result. So just to show you an example of how this can happen, suppose you were asked to add these four numbers together, 2.1 plus 2.24 plus 1.3 plus 1.23. So if you do this on your calculator, you'll get 6.87. And, you know, we look at these numbers here, and you can see that, okay, remember the rules for addition are we look for the number with the least amount of precision. You know, so this number, 2.1 and 1.3, there's only one decimal place. So our answer has to have one decimal place. So 6.87, we round that up to 6.9. This is the correct answer. But suppose instead we did this problem a little differently, and we said, all right, let's see, the first step, let's add 2.1 plus 2.24. Well, you get 4.34, but we have to round that to 4.3 because we're only allowed to use one decimal place here according to our rules. All right, so we'll keep that number 4.3 and hold it there. Then let's add up the second two numbers, 1.3 plus 1.23, we get 2.53, but again, this number 1.3 only has one number to the right of the decimal, so 2.53, we should then round that, we think, incorrectly, right, to 2.5. So now we add 4.3 and 2.5, and we get 6.8. But this is not the correct answer. The correct number is 6.9. So what went wrong here? Well, we incorrectly rounded and used sig figs on our intermediate steps here and then added up those results to get our final answer. That's not the way to do it. Do all of the calculations first, get a final answer, and then apply the sig fig rules to figure out the final answer. So that is it for Chapter 1. We will continue on with Chapters 2, basically, and part of the motion, the topic of motion in Chapter 1, we're going to combine that into Chapter 2. So the next lecture that you'll be watching is titled Chapters 1 and 2, and it's about motion. I'll see you then. Goodbye.